Okay. Hi, everybody. Welcome to the Diffusion Architecture YouTube channel. My name is Daniel Escobar, and I am hosting today a session with Mikhael Johanes. This is going to be a very exciting topic. It's about exploring machine understanding of architecture. So how do we use machine intelligence to understand architectural space? And Michael's going to present a few techniques that he's been exploring during his PhD, and he's going to show us how he's going about it. So first of all, Michael, welcome. And Michael is a PhD candidate at EPFL Media and Design Laboratory, specializing in AI-driven design and machine learning applications in architecture. His research focuses on the intersection of architecture, machine learning, computational design, and has contributed to various projects, publications, and exhibition. He participated in the 2021 Seoul Biennale with the installation Artificial Swissness, and authored an article on GANs, NLP, and architecture. He has also received multiple awards, and he leads a creative data and critical design practice with Frederick Kim Chando Kim, which was the previous interview on the channel. So, Michael, welcome. The floor is yours, and go ahead.
Thank you, Daniel. Thank you so much for your nice introduction, and thank you for the opportunity to talk in this great channel. So yeah, my topic is actually machine understanding of architectural space. It's coming from actually the diminishing discourse of space in the machine learning architecture. And the question is how we can refocus the notion of space with the ML methodologies. So it's also a response to how actually we capture architectural space in computation that usually favoring objective point of view, whether I try to focus more into how we can capture the experiential aspect of architectural space that usually difficult to be done in computation. So the focus here is to do that is to use isovist. It's actually a very old model of architectural space used in most of psychological and environmental research and also space syntax. So I use this as a way to create a machine learnable spatial data that can be extrapolated into 3 dimension. But for now, I'm focusing into only 2-dimensional data, which basically flatten into 1-dimensional panoramic image that make it super efficient for machine learning. And also I leverage basically the idea to leverage the thousand of housing improvement data that is becoming more and more available. So the idea here is how we can use anonymous architecture to create the understanding or machine understanding of space of architecture, but from ordinary understanding, not through seminal works of architecture. So the key here is actually the idea is like using the notion of representation learning. Basically, how can we learn the spatial pattern that we capture from isovist and then use the learned representation for analytical and generative applications. So the question is more like, what does this methodology, this machine learning, brings to the understanding of architectural space? So the hypothesis is like actually the structure of the latent space that is learned by the machine give us some different modalities of analytical and generative applications, which tied to the idea of typology, semantic, and the composition of architecture. So I will showcase these 3 plane of hypotheses with the 3 projects. One's dealing with the idea of a distance in the latent space to create the relational typology. The third one is how the directionality in the latent space tied with the idea of semantics of the space, and then how the discretization of the latent space can facilitate the generative design with the isovist. So the first project dealing with the idea of distance and how it relates with the typology. So as we know, typology is basically the idea of exercising similarity with the deep structure of the architecture. And this is like a very old sample from the Aldo Rossi studies of a Zurich Altstadt. And then how we can see actually with the typology, we study architecture not as individual, but as a statistical, as a collective phenomenon. And the idea of representation learning is actually essentially is also reduction, as if in typology basically try to reduce the data into its essential features in a way to have a meaningful information. So the question is like, what kind of typological logic that can emerge from learning the representation of isovist? So we use a variational autoencoder to learn the isovist data, and basically from that we clusters the data, and then we analyze the distance between these isovist clusters, and we come up with like basically 33 clusters, isovist clusters from the latent representation, and use them as a basis for developing what I call the spatial fingerprinting. And there are two ways of the spatial fingerprint that I propose. The first one, and it's very classical, like using back of isovist, basically improvisation from back of words methodology for document indexing back in the 90s. And also I want to leverage the topological relationship of the isovist by constructing isovist graph and using fact to graph to fact algorithm to create an embedding of the graph. So to see how it performs, I compare these two fingerprintings with also a more basic baseline fingerprintings method is basically using inception. They basically just use the image data and then use an inception embedding as a encoding, and then see how it can compares differently within this tree methodology. And then we can see like the isovist fingerprint focus more into the local morphology of the spaces, individual space of the floor plan, while the isovist graph basically less performant, because I think the graph to fact algorithm is not really perfect in this sense. But in the inception feature, pay attention more into basically the figurative aspect of the floor plan, like the graphical representation of the floor plan rather than space inside of the floor plan itself. Like we can see here how basically the inception feature search results is a bit like far away from what we wanted to have, while the isovist fingerprint basically managed to capture a few important properties, like such as the large opening on the north side, which and then also a small corridor in the south side. So basically, with this latent space exercise of representation learning exercise of the isovist, give me an idea that actually, if you're thinking typology as a problem of machine learning, it's boiled down into the idea of expressivity of the representation of the space, and also the learning algorithm that translate those information into latent space in a way that the distance becoming more meaningful. So it translates the logic of typology from like categorical into more like relational. So far we're talking about the similarity, which is expressed in terms of the distance in the latent space. Now I'm trying to focus more into the second project, which is try to see the differences, like how we can characterize the differences by looking at the direction of the latent space. And then we see in this very old example of floor plan interpolation by Alexander Klein, we can see there are like two axes, like the width of the floor plan and the depth of the floor plan, and how the housing floor plan like arrangement responding to these two axes. My take in this simple old example is actually we change the relation with the machine learning. Instead of having variables and then having data that responding to that variables, basically we have the possibility to discover a factor of explanation automatically from the data. So based on these two hypotheses, basically I try to operate this idea of how can we get this unground this factor of explanation by using manifold hypothesis and also this distributional semantics. So the idea is like there is a possibility to infer meaning just from the distribution of the isovist. So it's not like through external labels such as supervised machine learning, or using in the BIM models, we always have labels to ground the semantic dimension of the architecture. But can we get meaning only from learning the formal distributions of isovist? So I look deeper into the latent space, and basically there is an algorithm that can be used to discover this kind of like prominent directions in the latent space. And we use that, and then we managed to discover few statistically significant direction in the latent space that eventually it has some architectural meaning. Of course, it's not really something that complicated. It's much simpler, like only proximity to the wall, to the corner, also to the openings, and also how it responds to directionality, the cardinal directions like south and west, north, west and east, and something like that, and also about the size of the hypothesis. So it's in the images, in the image domain, it's easy to read, like, back in the days of GAN interpolations, we have this like faces with and without glasses, old and young. So basically, it's similar logic. Like, we try to find the semantic differentials in the latent space of the isovist. So with the semantic differentials, we can project those semantics by basically just like a vector projections in the high dimensions and project it into the architectural space. And indeed, it shows some results, like for example, if we use the direction that correspond to an opening in particular directions, it will fires if close to such space that have particular directions to the particular qualities that corresponding to the directions, like the openings or the size. And also always divide into the cardinal directions, because that's what is the majority qualities that can be inferred from the data. But if you look closer, actually, it's a way to find kind of flexible way of reading the space. So the reading of the isovist is not like numerically defined, but more like statistically inferred. So if you're talking about distributional hypothesis, is basically the idea is meaning is created by statistical structuring of differences of isovists. And we try to extrapolate these results to unseen data. So basically, we train the model with only housing typology, and then how the question is like, what is interesting, like how if those model that is trained by only ordinary architecture is used to see modernist architecture or classical architecture, and it does it can generalize a bit, and then it showcases like how the boundary and openings can define the space that it try to express. And like, for example, here in the Villa Rotonda, like the elongation of the space, it can be used to showcase how the alignment of the openings like connects the loggia of the villa with the center of the space. So this is basically for me is a demonstration how the directionality of the latent space can be utilized to infer some meanings in the formal morphology of the space that is captured by the isovist. So the meaning is not like explicitly defined by ourselves, but basically statistically inferred by the machine. So we jump a bit from analytical to generative, and also we change the modalities of the latent space from continuous to the discrete. Why discrete? Because if we look at the history of architecture, like very old, the idea of discrete is really always tied to the idea of generating architecture, like how actually by discretizing, like decomposing architecture into computable units, it allows computer to recompose those elements to create new architecture. The problem is like by having discretization in the data space, like as a voxel or as a discrete elements or a discrete rows as in SEP grammar. So there's like two ways of discretization, like explicit in the material ways or the formal ways, or through the logic of its constructions, which is the algorithm. Is also a demonstration of the logic of the discrete. It's unfortunately redefined architecture into its rigid logic. So instead of creating architecture as we know it, it's basically enforced the logic of discretization into architecture, which is, of course, it's maybe one can argue is an expression, but also a limitation of this logic. So the idea here is how we move the discretization logic of architecture from the data space to the latent space by using discrete representation learning. So I'm using a VKVIA, basically a similar algorithm that being used by GAN, basically try to learn isovist representation, not into a single vector, but into a set of codebook that can be rearranged in different way to represent a data. So the logic here, once we learn a vector representation of isovist, we quantize the vector representation and then we store it in the cells, like let's say 1,000 words, and then we can use those combination of numbers in different ways to express that. And it proves to effectively improve the performance of autoencoder. Like for note that the algorithm is not trained with this data set. It's only trained with housing data set that mainly orthogonal, but by using quantized VKVIA, it can generalize to reconstruct a non-orthogonal floor plan. So it showcases how the quantization actually help the generalizability of the autoencoders. So having the VIA to tokenize basically the isovist. We use isovist series like interweaving the movement and isovist as a series. So basically we create a code like a series of numbers that represent both isovist and movement into a floor plan. And then basically we can represent an experience of walking through a building with this method. So using this, we have the possibility to learn space not as a configuration, but as an experience of walking through buildings. So by using this, we sample the floor plan from the dataset by using the sequential floor plan, and then use a transformer, decoder only transformer, to learn the sequence, and then use the encoder of the VKVIA to decode back the isovist, and then use it to construct the architectural space that expressed in the sequence. So the results is quite interesting because it never generate full configuration of architecture, but is basically a kind of memory of the experience of walking through the floor plan, and then kind of like being recombined and combined together to create configurations. So here, for example, like you can see like reminiscence of like studio like typology, like with the bathroom with the small corridor, and then big bedroom with the large windows. So indeed, it can learn it can create architecture through the sequence of movement and space. But the thing is, like, because it sees architecture not as a configuration but as a journey through spaces, so it has some freedom to interpret the dataset in different way. So it has some creativity in a way that it it doesn't see the process of design as a single step, but as multiple steps that the first step are the condition of the second step, and so on and so forth. So it's, for me, it's quite interesting way of thinking how we actually create a machine that dreaming architecture through it one point first person point of view instead of a top view that we used to have as an architect to design a floor plan. And another aspect of machine learning is the ability to enable transfer learning. So basically, once we have a working model that is large enough, we can leverage the knowledge that has been learned from the old model, and then fine tune it with only few datasets. Like here, I try to fine tune the model again, like the model that has been trained with the 4,000 floor plan data, with housing data, with valid and villas. And then the results are quite interesting because, of course, I think it can capture the local morphology of the individual spaces of the Paladin villas, but it doesn't capture the larger symmetrical logic of the building. Which for me is also an interesting exercise in this regard, because then it have a different interpretation of Palladian architecture. So basically, instead of having very rigidly divided spaces, it's basically compose the maze out of it. And also, because of the attention span of the transformer is rather limited, because I'm not using a big transformer. It's just a transformer that is small enough to be trained in one GPU. So it's only like can learn like 15 sequence of an isovist. So it creates this overlapping scheme that sometimes give you some idea actually how to play with levels of the architecture. So it's basically, the overlapping is not something that is frowned upon, but it's more like a feature that give a different interpretation of the results. So another exercise, we go a little bit more extreme, like only having 3 floor plans from the Miss Van der Rohe pavilions, and then it's still able to learn the typical architecture of the pavilions. And we see here like it results in completely different configurations, like with the freedom, with more free movement, and the interlocking space in the freestanding wall that characterize the Mies pavilion. Here we see like it has more freedom with the movement, but also more overlappings, because the question of the scale, like it has in order to generate this kind of configuration, you have a longer sequence that then you will forget always the sequence that you have in the beginning. But the juxtaposition of these interlocking spaces give another layers of interpretation in this regard. The problem with fine-tuning with a very small dataset is the memorizations. That is always a problem with machine learning system, I guess, with a small dataset. So I think this is more like technical problem that we need to figure out in the future. So this is my last slide. Is showcasing the infinite wandering or generations of the 3 architecture from the datasets. The left one is the housing datasets, and the center is from Palladian villas fine-tuning, and the right one is from Mies van der Rohe pavilions fine-tuning. And then you can see like how it differs from one to another, even though the model were mainly trained based on the housing typologies, and it showcased some expressivity of transformer in basically learning everything sequential. It's not just learning words, but also can learn everything, including architecture. So I want to close my presentation with a few concluding statements. So basically, these three experiments showcase like how ML changed our understanding of architectural space through representation learning of isovists. So the idea that like the structure of latent space determine the analytical and generative modalities of architectural space, kind of demonstrated here, like how it changed the typology from categorical to relational, and how it changed the idea of semantic from externally referred to statistically inferred, and how we can decompose architecture not explicitly through algorithm or components, but through implicit in the latent space, which improve the generativity and learnability without having these discrete artifacts uh, in the architecture. So thank you so much.
Awesome, Michael. Thank you for a great presentation. Really interesting work. Um, if you don't mind leaving this screen on just for now, because I have a few
Yeah,
questions about this, but this is really
yeah,
interesting. And I think the idea of taking like the spatial concept of architecture and embedded it as a sort of like sequential model, right? Or as a sequential understanding of the space that can be used generative. Can you maybe talk a little bit about like any sort of unexpected generations or sort of like unexpected results that you had once this work was done? Maybe like prior thesis and like exploring like the idea of developing this, but maybe some unexpected results that you found through this.
I think well, before I go to the unexpected, I think in the beginning I actually want to have more freedom in terms of the sequence. Like instead of limiting the sequence into this rigid network, I want
Mhm.
to have a more freedom steps. So I have a more stochastic. But I think in theory it could work, but technically it's more expensive, I think, in terms of like computational resource. So the result is not really good in the first experiments. So that's why I switched to this rigid grid to this grid network, and then do the sampling. Uh, the unexpected is actually, I didn't show it here, but even though in the dataset you don't have isolated rooms, because I clean up the dataset, like I know that there is no single data in the dataset that have this solitary space.
Mhm.
Somehow, sometimes the algorithm generates that kind of space. I think you can see here. I think in the like, oh, like here, I think you see like there's like individual space that
Yeah.
has openings, but I think one or two equation, it really creates the like squarey box. So it's kind of like extrapolate from the data set, like it generates something that you didn't expect in a way that it locked itself. The thing is like because the movement and space are tied together, once you
Mhm.
get trapped, you cannot generate something anymore. So it's
Yeah.
so it's all it's something that I want. It's kind of like something unexpected in kind of theoretical way, like the architecture.
Yeah.
What kind of architecture that can be generated with this approach? Like it's not something that is neutral, Yeah.
Yeah. No, and I think it's really interesting because it is a different approach of like generating like a floor plan, right? Traditional, let's say like other machine learning approaches to generate floor plans, they're usually based kind of like more on a top-down, one-shot generation, right? So it's kind of like you
Yeah.
train on a whole bunch of floor plans, and then it's just gonna generate based on what it learned, like a top-down image. I
Yeah.
think this one, I like the trajectory aspect about it because it does open, like what you said, like these possibilities of generating something that maybe was not included in the data set, because it's just a sequence of statistically determined steps. And maybe talk about like is the walking of let's say like the movement of the transformer like
Mhm.
position, is that something that you're presetting, or is that something that is also getting generated autonomously? Yeah, like
This
that
one.
stepping. Yeah.
So basically, this the if you If you look at the paper, actually I mentioned it. Basically,
Okay.
it's a random walk, but not random walk. It's a biased random walk that implemented in the not to fact algorithm. So basically, in the not to vec algorithm, there are like two ways of having random walk. The first one is like I call this like DFS like behavior. So basically, it always it's biased. You set up the parameters in a way that it always tries to get out of the original starting point.
What did you say?
So
DF, you said DFS, like, so
DFS,
like depth first
depth
search?
first, yeah. So
Okay, can
basically,
you
it
explain a
always
little bit about, yeah, go ahead.
So in the not to fact algorithm, the way you walk through the algorithm will determine the kind of information that you will learn from the network. So the author of the algorithm decide to to control that walk, to
Mm-hmm.
bias that walk, not just pure random in the beginning, because the I think the original paper is not to fact. I think there's like before not to fact there's like one paper that only use one mode, which is basically 0 degree random walk, basically just random, pure random. But this author create these two version of walk in a way to bias the walk, that one is more local. Basically, you create a walking that just like going locally like this, so it will emphasize on the neighborhood relationship of the network. But if you go working like this, it emphasizes on in the more like big structure of the network. It learn a more global features of the network. So here I implement that work not for learning the network, but learning the space that is represented while you are working in the network. So basically, this is something that is random that I also want to improve more. Like, I think there is a more intelligent way to drive this movement. Like maybe in giving a little bit more like deterministic algorithm to make it more believable, for example.
Mm.
Like not like just wandering like crazy in one space. So yeah, this is my answer to that.
Yeah, so it's almost like, I guess, like the approximation of this type of approach is like, how do you get close to how like a human would move in a space, right? Like
Yeah.
how do you, how would you simulate that through some sort of I guess, like step in through the space, and how do you encode that, or how do you simulate a human? But it is an interesting approach, though, because it does give you kind of like maybe unexpected walks that a human would not take, let's say, or that
Yeah,
it
yeah.
wouldn't get stuck in a loop somehow. Um, so maybe now let's talk about, like, have you explored this in section as well, or is it only kind of currently in floor plan?
Sorry, explore what?
In section, like a sectional isovist,
Oh,
let's say.
no, I think I want to actually explore further into 3D isophysics, because that I think makes more sense. Because I think there is a floor plan data that is good enough that I can somehow extrapolate into 3D domain by a simple extrusion and stuff like that.
Mhm.
Because the thing with the 3D isophysics, you cannot use a normal convolutional network, because for me it doesn't make sense, because you will have more data in the polar coordinate of the spherical, so it has to use a geometric PyTorch, the graph neural network to capture this like this spherical isophysics. So that's one direction that I want to take. In terms of section, I think because this is talking about movement, and
Mhm.
movement is always in the horizontal plane, most of them. Uh, I think it's makes it does make more sense if I extrapolate this into 3D domain instead of using section. I
Mhm.
think more into stack of floor plan. That makes more sense probably. So we can
Yeah.
create like 2.5 dimension of a floor plan.
Yeah, yeah. No, that's super interesting too. And so let's talk a little bit about I guess, like, what it took for you to get this data set, and how did
Yeah.
you figure out how to encode it? Like, was there like a lot of data set preparation that went into this?
It's actually gradually because I started my PhD in 2019.
Yeah.
So back in the days, the idea is like, oh, I have isovist data, and there are this kind of bunch of autoencoders. So I start simple, like just the analysis. Like the first two experiments are like the 2021 and 2022. Like this basically just focusing on the analytical part, and then once you get more into it, and then you look more, no, like you understand more, and then you kind of like going deeper into this idea of like, okay, there's continuous and there's discrete, and then like with also reference to different papers. Like I think it's inspired a lot by actually Vicky Gunn. Basically, a similar principle, just different domain. I wrote in the paper that it's basically a similar paper, just different domain. It's basically logic is similar using autoencoders to quantize a space.
Hmm.
In Vicky Gun, you use autoencoder or GAN to quantize image. The difference is the sampling, because of course with the image you basically just doing this kind of like scan line movement, but with architecture you cannot do that. So the innovation here is how to combine different algorithms together to basically kind of convey the architectural logic of it.
Yeah,
And
yeah.
yeah, and actually technically it's doable. I mean, it's not something that you have to build from scratch. Like there are components somewhere there that you combine together to make it work. So it's a very fun project. The thing is with why I use isovist as well, not images or videos, because it forces you to rewrite the existing algorithm to your data. So you cannot just use it. So you
Hmm.
really learn the logic of it by rewriting that into your data set. That is kind of like exercise that I think it's quite stressful sometimes, but it's really rewarding if you make it work.
Yeah, no, that's a good point because you do have to pull things from somewhere, understand the logic. How do you actually input the data, right? Like, how do you actually
Yeah,
structure the data so the algorithm reads it? How deep is the like how many channels is the image or whatever your kind of the data set is working
yeah.
with? Um, so no, so I guess like the interesting part that I found about this is that it's also you compare like two types. You said you went from analytical and then generative. Was there like something unexpected or maybe like some sort of conclusions that you can take away from the analytical, like where you compare like I think like the Palladium
Hmm.
Villa and then like the Mies van der Rohe Pavilion.
Hmm.
Was there things that basically from seeing the results of the analysis process with AI that as an architect, you can understand something new from that architectural floor plan?
I think the insight is maybe as an architect not yet into that deep insight, like because the kind of like analytical um, modalities is very basic right now. Like it's like feeling narrow to feeling large, like having no opening to have a large opening and stuff like that. But I feel like in the future, if we have more data, because the data set is rather limited, it's only like 4,000 data with only also the autoencoders that I use is very small, like very small. Like I feel like once you scale it up, and then you can get a more like a data scientist, and then the thing is like you cannot just use this kind of method. I think you have to improve your visualization strategies to see the subtle changes in the data set, in the results that can have some kind of like mixed signals. I think for me, what is challenging is not actually to see what is prominent, but I think with machine learning is to see the weak signals, like how to see this. Because you, with the machine learning, you always go with the dominant, like the with the the law of large number, you're always going with the average, and then how to push, or how can we equip people like us to use otherwise, not to see the trend but to see the potential. I think that is yet to be done. Like, how can we find this like a very fine signal that is not just noise?
Yeah.
Yeah. And um, I think what also another finding in this kind of thing, for now, I think this notion of discrete and continuous is still a kind of separate, because once you have the discrete, you are lacking interpretability. Like, I'm losing the directionality once you create this kind of discrete representation. I try to visualize the vector that being constructed by this method. It doesn't have any sense. There is no pattern. So I think if there is a way to combine these two modalities, like you can generate while you understand, I mean, not me, but the computer can have interpretation, that would be something that could be cool, I think, because then we can delegate more command to the computer and encode more high level instructions to them.
Yeah, can you talk a little bit about that? So you're saying there's some sort of I guess like gap between like discrete and continuous, right? Or in
Yeah,
this representation, and
yeah,
the representation that you're pursuing in like the isovist example, it's like a discrete representation of space.
yeah.
And what does that mean? Like, what does that mean in the
Oh,
sense of your
uh,
focus?
my what I mean with discrete and continuous is not in the data domain. The isovist itself is of course discrete, but I treat it as a continuous. It's basically 256 pixels of isovist, so
Oh, I
it's
see.
almost like an image. But in the latent space, the latent space itself, there are like two principles of a latent space. The one is continuous, in which you can infer, in which the distance and direction of the vector in the continuous latent space has meaning. Like, it can of course with the GAN, you know that you can create analogical, like arithmetic of the latent space. You can plus this plus minus, you can
Oh, you
subtract.
mean
Yeah,
to like actually
yeah,
navigate through it in some
yeah, yeah,
direction? Oh,
yeah. You can
right.
interpolate, and then you can, and there are meanings, like you can basically, the technical term is like, you can parameterize manifold into the latent space, like the color or the bright or the position of the isophysis and stuff like that.
Hmm.
With the discrete, it has different logic. It doesn't create continuous vector. It doesn't like having this a very compact vector space, but basically dissect the vector into smaller vectors and then store it as if it's a code. And then you basically represent the vector not as something that you sample statistically from the latent space, but something that is almost like Lego, that you just like uh that you just like pick up from the code book and then rearrange in different ways to have a meaningful information. And then somehow this piece of information, even though it translated back with the decoder, like something that we can see as an isophysis, this code itself doesn't have any meaning with the, I mean, it's with, I mean, the computer doesn't have any interpretation of that. So there is a gap between being able to generate and being able to understand for me in these experiments, because if we want computer to understand, we have to regulate the latent space with assumptions, and then we lose a lot of information. So that's why we lose a lot of information here, like it cannot reconstruct a lot with the VIA. But in order to make a strong generator, we have to get a model that can compress and that can generate as much as possible information, which is sometimes compete with the objective of having regulated latent space. So in a sense that in the VIA latent space is sparse, unregulated, and empty, where the latent space of the VIA is almost like a very compact. even though it's high dimensional, it's very compact. Like everything is just within 0.0 something.
Oh yeah. So
Yeah,
it's
and then
easier
it
to
has,
sample it and you can interpolate. And you
yeah,
showed like I think you showed and this kind of makes sense now that I'm looking at the image where the VAE has this more blurriness to it.
yeah,
Uh, which like like the kind of like original paper for like the VAE where they have
yeah,
like the numbers interpolate them. You can see kind of like that interpolation and you see how
yeah,
the blurring is merged. I also explored around like VAEs before.
yeah,
And there is this sort of like kind of soft or let's say blurry kind of like in aspects of the generation about it, which I wonder if that's something that I guess like do you see like any other approach of doing this, or is this something that you kind of have I don't know, like how do you see this as affecting like the work that you're doing, or is it just more like a technical issue?
I think it's something that I want to pursue more because I think there is more and more research about how to combine these two representation together.
Mm-hmm.
Especially with the large language model, with the visual language. I mean, with the visual language model, like how do we combine different modalities?
Mm-hmm.
So the problem with in those areas, like even though it can generate a lot of stuff in high quality and then can infer many stuff, but the interpretability is still like very almost like an art, dark art, you know. So
Mm.
so uh, there is a research into that directions. I think the next challenge I think is to collaborate with the engineers to really understand how we can kind of translate this idea like a semi-technical idea into something that is working, because the problem is like uh, of course the majority of of the algorithm are developed for the generic domain, like either visual language or audio. But the problem with architecture is we always work is kind of specific data, no? Like a spatial data.
Mm-hmm.
And then like now we are slowly moving to the 3D domain, but the 3D is sometimes is also something like more like object like 3D, and then how we can open up like let's say there is like another way to represent space using nerve. I
Yeah.
think you know that. And to move the nerve from this just a solid just one object representation into more like continuous. I think there is one thing that I really curious how to use nerve in that way, in kind of like using similar way that I generate the sequential space but in the nerve space. That would be something interesting.
Yeah, the I seen like I remember like when I first started messing around with like 3D stuff is that the one of the ways to represent like 3D spaces, let's say, and that this was done by the Autonomous Vision Group in I think it's in Germany, so at one school in Germany. But like the original kind of like paper that was using like this sort of idea of exploring like 3D space was like occupancy networks.
Mhm.
And what they would do is like essentially take like a volume and just populate it with like random set of points. And then based on those points, they would let's say predict whether the point is occupied or not, right? So then you would create like
Yeah,
points that are like solid or not. And that was like one of the approaches that I was like, okay, like that makes sense. And that seems like what is working with, let's say Tesla. Like it seems like Tesla's employing that to understand like space and things like that. And some other like applications in robotics seem to be focused also on that. Like how do you build like a voxel representation of the world that is easier to detect kind of like walls and things like that in some way that is not necessarily architectural like in how you're
yeah.
trying to approach it, but it's more of like being able to detect like these 3D boundaries in some way.
I think that's the next directions, like how we can kind of translate our representation of architecture, like now more like geometry heavy, um, like like we represent wall as a geometry, as a NURBS or meshes or something like that. And how can we make it like operational in neural network?
Hmm.
Because it's not a native language for neural network with the mesh or something like NURBS or I mean, Rhino geometry. It doesn't work. That's why I'm
Yeah, yeah.
interested in nerves. Sorry, in nerves. Not nerves, but nerves. Like this neural representation of 3D. Like whether maybe in the future we don't edit in Rhino anymore, but I edit in this kind of like neural editor of 3D.
Yeah. Yeah,
Yeah,
that's an interesting point. I think that's kind of like an interesting area of research right now in like this sort of computer vision field where like how do you edit these like nerves, Gaussian splats and things like that.
yeah,
And they seem very applicable to like I've seen like now great demos of uh, being able to generate like some sort of Gaussian splat and then bring it into like Unreal Engine, or there's like now apps developing online. Like Play Canvas has like a Gaussian splat editor where you can like select the points, remove them, and like clean up. So it's still like a long way, but it is kind of interesting to see if that would translate to an actual geometry that can be used like in architecture. I'm not sure.
yeah. The problem right now is the interactivity. Like we
Yeah,
love to have the immediateness of having click something and then we have the effect right away in our screen with the
yeah,
CAD
yeah.
modeler. And right now with this kind of neural networks representation, it's still there is a gap between that between intention and results. So a long
And
way to
Michael,
go. Yeah,
yeah, definitely. Michael, there's actually a question here on the live chat
yeah.
from Reza R. He says, "Hi, Michael. I read one of your article regarding with map trajectories. Is this development project based on that studies?"
Sorry. What trajectory?
He's talking about regarding with map trajectories. He
Heat
read
map.
one of your articles with map trajectories, and then he says, "Is this development project based on that studies?" I'm guessing is this
Oh,
another project that you worked on? Or?
not sure what trajectories. Wait a second. I'm thinking. Oh, is it like a few years back a paper like
Uh,
before 2019?
I don't know, Reza, if you
Because
have a if you have an
because
answer to that.
because in before I'm doing my PhD, I did a lot with like movement simulations, like in the
Hmm.
complex built environment. So yeah, I have few experiments like how to model trajectory using basically sorted spat, but not sorted spat algorithm, like a search algorithm. It's just like
Hmm.
the simplest but the quite cheap way to generate trajectory. Well, it's not really related to that, but I think the idea of uh, trajectory is always in my mind in general because I want, for me, like the idea is like whether our experience in architecture, like when we move through the buildings and stuff, can affect the way we design a building. It's always kind of like some kind of in the on the back of my mind, like try to come up with idea that make the architecture that we design get closer to the user experience instead of just a strong ideas of geometry. So I hope it answered the questions. But this paper is basically kind of like snowballing from the PhD research that I did, and then of course previous research always inspires my my work.
Awesome. Okay, he didn't answer, so I'm hoping that answers your question, Reza. Okay, Michael, we're at the hour. This has
Yeah.
been really interesting and fun.
Can I stop
Thank you
sharing
so.
this?
Yeah, you can stop sharing.
Yeah.
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 So we're up to the hour, so it's been really interesting and like fun conversation, and also the way that you're approaching this idea of like using like an isovist. Like I haven't seen that in these types of approaches before, so it's really cool. Do you have any advice of for young practitioners or architects coming into like the like this space, like computational design, AI related space in architecture?
I think the only advice for me is like to start um, as early as possible when you're still in college and have a lot of times to learn many stuff. Because sometimes when we when we are already practicing, sometimes we don't have any time or motivations to do that anymore. I think when we were young, I think that's the moment that we kind of like decide our future, what kind of architects that we want. Like I was coming from a more like traditional background, like trained as an architect, but before doing architecture, I want to be a computer programming. So it's always I want to have to build my own like computer video games, but it didn't happen
Mhm.
yet. So hopefully in the future. But yeah, and then as an architect, I just like develop in the other way, like more like the theoretical and also the practical. And I mean, I'm really grateful that I have multiple kind of inputs. So it's not all focusing on just computational design, but
Yeah.
also I have a classical, I like more like a strong background in architecture. So it's kind of like complement each other and then give me this idea of like combining different things together. I think for me, what excites me is not something, it's not particularly one thing, but the meeting point of two things together.
Hmm.
Interesting.
Yeah, the intersection is always fun.
Yeah.
And just to close it off here, what are you most excited about? I guess like this area of like AI and architecture for like the next couple of years. Like, is there things that really excite you at this moment?
Because I think the for me this is reflected in my title, like this combination of analytical and generative, because it's usually two things that kind of
Mhm.
separate in computational agenda of architecture. Like if you know like fields like space syntax, it's like focusing heavy on this analysis of the space, and then the generative design is just coming up with the new way of designing stuff. But how we can kind of combine these two fields together with the machine learning that can absorb few complexities in between, I think that would be interesting field to discover.
Awesome. All right,
Yeah.
Michael. Thank you so much. Those were great answers. Thank you so much for being a part of this. Really enjoyed the presentation and conversation. And I'm looking forward to seeing more of your work. We'll stay in
Yeah.
touch.
Yeah. Keep in touch. Thank you so much for having me.
All right. Have a great day. See
You
you.
too.